week 9 topic, which is electric fields. So we're going to look in electromagnetism course. You have electric fields, you have magnetic fields, and then we combine them at the end. They get a little bit trickier. But we need to cover the electric field component. So could you please turn to the inside page? And I am screen capturing, and as soon as you guys get cold, somebody can turn off the aircon. Okay? So, electric charge, difficult to define. So is mass. Mass is difficult to define. What they have decided, our current understanding, is that masses produce gravitational fields, which can then influence other things that have mass. So the Earth creates a gravitational field. We have mass. We're being influenced by the gravitational field of the Earth. We can calculate things like field strength. At certain points, the strength of the field. It's measured as force per unit mass, newtons per kilogram. It's very analogous to electric fields. Anything that has an electric charge creates an electric field. That can then influence other things that have charge. It will exert an electric force. Okay? Way back when, it was discovered that there were two types of charge. And in fact, I've said this in year 11 and year 10 and year 9. They grabbed a piece of amber, which is like tree sap, and they rubbed it on a rabbit pelt. The ancient Greeks discovered that the amber now had this rare quality that it could pick up little bits of confetti, or that your hair would stand up trying to grab the amber. They called this phenomena electros. It's the Greek word for amber. So all your words for electricity, electrical, electrocution, electron, electronegativity comes from the Greek word amber. You may have done this in year 8 when you played with the different types of glass rods and plastic rods and acrylic rods and Bakelite rods, that sometimes you can create a repulsive force and sometimes you can create an attractive force. So they came to an agreement that there was like charges and unlike charges. Somebody made the convention that one was positive, one was negative. Okay? They discovered that it's not being created or destroyed, it's merely being transferred from one object to another. So we can move charge about, things can develop a net positive charge, net negative charge. They then figured out that the development of the historical development of the model of the atom. All right, cool, atoms have a net neutral charge. They can become positive ions or they can become negative ions. And then Rutherford figured out the electrons are the ones that can be ripped apart. The positively charged protons in the nucleus, they stay remaining. Then, who was he? That was Millikan. Robert Millikan was able to figure out that the smallest unit of charge is that many coulombs. We'll get to coulomb in a minute. It is the fundamental charge. You cannot get a smaller quantity than that number. Okay? You can never find in nature a chunk of charge that is not that multiple, and that is the smallest multiple. So a 2 negative chlorine ion would have a charge of 2 lots of that negative. Okay, a +2 ion would be 2 lots of that positive. Okay. Since then, they have discovered that there are subatomic particles called quarks, and they have fractional charge, fractional 1/3, fractional 2/3, but it's never been found existing on its own in nature. You can never go, oh look, there it is, 1/3. No, they're always trapped, stuck together, making quarks, up, down, top, bottom, charm, and strange. We will learn about quark model later towards the end of the year. So, positives and negatives cancelling out. Then this is all just chemistry and lower school science. Conductors, those that allow charge to move, well, those are going to be free electrons, delocalized electrons that can move through metals. With insulators, they are going to be your covalent molecular, your non-metals, your covalent solids, because the electrons are involved in chemical bonds. They are keeping the atoms linked together. They cannot bounce around delocalized. Okay? And then semiconductors, you can basically get a certain amount of both metals and non-metals and semi-metals, and they have weird properties that they can sort of be intermediate. Let's get to this bloke here. Now, this is Coulomb. Look at it. I like this photo of him with his nice Fonzie jacket popped up, looking good. He was the first guy that quantified electric charge, and it was named after him. He was playing with huge amounts of net charges. So when he was sort of rubbing rabbit pelts on acrylic glass bricks, he was stripping off billions and billions of electrons. But he didn't know it because he was before Robert Millikan. So he said, all right, I've now accumulated a 1 Coulomb charge. And I can now accumulate a 1 Coulomb charge on another insulating block, and there will be a repulsive force. And he played around with varying the net charge, varying the distances of separation, how many newtons for how far apart, and he came up with this equation known as Coulomb's law. And we're about to draw Coulomb's law right now. So, here's the thing. Where's my little style? Thank you, stylus pen. If you had Q1 equals charge 1, measured in coulombs, and Q2 is charge 2, also measured in coulombs, and you separate them a distance r, measured in meters, then you will get a coulombic force measured in newtons. And so he was the first person to give the SI unit for electric charge, and so it was named after him. Capital C, named after Charles Coulomb. The equation is the coulombic force is K Q1 Q2 over R squared. It is very similar to our gravitational force, which is G M1 M2 over R squared. It depends on the product of the charges. The greater the fundamental unit of charge, the greater its effect. And then it's an inverse square. So the further you get away, this force reduces. It is exactly the same as gravity. The greater the fundamental unit of mass, the greater the gravitational attraction. The further apart the two masses, the weaker the gravitational attraction. Here's the unfortunate thing, gentlemen. This was once in year 11. And when they changed the syllabus in 2015, they took this section out of the year 11 course and they threw it into the year 12 course. And then they decided that, you know what, this K, which is known as Coulomb's constant, it has a unit. And you're going to write this 8.99 times 10 to the 9. It's a constant of proportionality, right? It takes the fundamental units of charge divided by the fundamental units of distance, and it spits it out to something that's kilogram meters per second squared, the unit of Newton. So it's a constant of proportionality. It has the units of Newton, meters squared per Coulomb squared. So let's just look at that number. It is quite large. If I could get a Coulomb of charge and place it here on the table, and a Coulomb of charge and place it a metre apart, then the repulsive force is going to be 9 billion newtons of repulsion. They would go flying away. And in fact, it's not possible to accumulate a Coulomb of charge in any one point. You figure out the electron is like 10 to the negative 19, so to get a Coulomb, you need the inverse of the fundamental. You need like 10 to the 20 electrons. You cannot put 10 to the 20 electrons in one point in space. While you're trying to push them all there, they're going to start racing apart, and you'll have this sort of sphere of electric lightning bolts coming out. So it's not really possible. But just think, if you took the fundamental unit of charge next to a fundamental unit of charge separated by a fundamental unit of distance, 9 billion. Now, compare that with gravity. If I put a fundamental unit of mass, one fundamental unit of distance away from another fundamental unit of mass, what was the force of attraction equal to? The gravitational constant, 6.67 times 10 to the negative 11. So you're comparing gravity, 10 to the negative 11. This constant is 10 to the 20 times greater. Electric and magnetic forces are much, much stronger than gravity. Gravity is the weakest of all forces. For any significant effects, we need to have a shit ton of mass, a planet or a star's worth. Have a think. I thought about swearing before I said it, and I'm like, yep, these kids can handle it.
No one
You did this. You rub the glass rod, right? A couple of wipes of the rabbit pelt, and you can pick up pieces of paper, the little confetti. You are basically overcoming the entire gravitational attraction of a planet. It's not that hard. Look, gravity's weak. All right? It's not a very strong force. Okay? Now, here's where things get trickier. So they said, hey, let's put this in the Year 12 course. It turns out that the Coulomb's constant, when he derived it, it just linked charge and distance to force. But it turns out that this Coulomb's constant is derived from a physical constant. Coulomb's constant is actually now known as 1 over 4 pi epsilon naught. Epsilon naught is known as the permeativity of free space. And it has the units, or the value, of 8.85 times 10 to the negative 12 farads per meter. Don't worry, not in course.
What's a farad?
A farad is the unit of electrical inductance. It's a unit of how much charge that you can store. Basically, the permeativity of free space is a measure of how electric fields travel out in a vacuum. Okay? As simply put, it's how electric fields permeate through space. And the great thing is, this is a constant. It's a physical constant. It's the same here. It's the same on the other side of the solar system. It's the same on the other side of the universe. Aliens that exist and are trying to figure out the laws of nature, on their data sheet for their young aliens going through Year 12 alien physics, they will have the same physical constant. In your data sheet, you have some physical constants. Those are things that never change, no matter where you are in the universe. Those are the speed of light in a vacuum, the charge of an electron, Planck's constant, the gravitational constant, the electron volt, the electronic constant. Okay, in your data sheet, it's called the electronic constant, but it has the same symbol, epsilon naught. Okay? 8.85 times 10 to the negative 12 farads per meter. So unfortunately, when you come to your Coulomb's law, it doesn't have K, it has that. Okay? So your Year 12 level equation is the Coulombic force is 1 over 4 pi epsilon naught times the product of our charges divided by the separation squared. Okay? It's just a little bit nastier.
We have to express K as such a
So don't use K at all. In your data sheet on page 3 at the top, it's got that in blue. So this is what we need to use. Okay? Now, just be careful. If you're not given a specific object, if you're just asked for the force between two objects, you just need to remember if they're like charges, you write attraction, so many newtons attraction. If they are, try that again. If they are like charges, you write repulsion. If they are unlike charges, you write attraction. If it's saying, what's the force on electron labelled A, then you could write left or right or up or down if it's given in a diagram. Okay? So, could we consider an electron? Here he is. In 3, 2, 1. Here is an electron. I just spawned him into space. And now, 1 centimetre away, I spawn another electron. they are going to repel. And even Newton was onto this. He said, action, reaction, you need two objects. You'll get FA acting on one, FR acting on the other. So gravity is an example of Newton's third law, action, reaction. Two masses, two forces. Same here, two objects producing two electric fields. They each interact with the other's field. They feel a force. So they would go flying off at equal magnitudes. All things being equal masses, equal charges, would be perfectly symmetrical. Obviously, yeah, this guy just wouldn't be stationary. You would never see him stay stationary and the other one go pa-choom. That would imply that this guy had infinite mass. So they go off racing apart. If you were ever asked to quantify the force, here we go. 1 over 4 pi epsilon naught Q1, Q2 on R squared. You can, once you've written that, you can just throw the Q's on top. You can just make it one fraction. The data sheet obviously has them separated. Well, no, just they are two separate objects, so keep them separate. 4 pi, 8.85, 10 to the negative 12. Don't forget our R squared, 0.01 squared. And we get 2.31 times 10 to the negative 24 newtons repulsion. Okay?
Is that pretty significant relative to mass?
You're reading my mind. Get out of my head, Charles. We've seen the memes, yes? No, Charles. Yeah. Get out of my head, Charles. Absolutely. This is on a macroscopic scale. You wouldn't even feel that. But if you are an electron that has a mass of 10 to the negative 31, then yes, we could figure out your... I'm not going to do it, but you're on the order of 10 to the negative 24 over 10 to the negative 31. That's going to be the order of 10 to the 7 meters per second squared. So yes, they would start racing off very, very fast. But as they move apart, the force drops as per the inverse square. So as they get further apart, the force decreases, their acceleration decreases. Eventually, when they get an infinite distance apart, force becomes zero, A becomes zero. They travel off with some speed forever into the universe, never to be seen again. So let's bring this back. Let's play the tape backwards. Imagine I took two electrons from either sides of the universe, infinite distance apart. And as I bring them together, they start to repel. So I've got to start pushing them harder and harder. I'm doing work. I'm applying a force over a distance. And as they get closer and closer together, the force increases. And then I get them to 1 centimetre apart. And I hold them there. All that work that I've done is now stored electrical potential. And we have a measure of the energy done on a charge. That's called voltage. So we could literally describe the electrical potential of these two charges. They are in a position that they don't want to be in. They would have a certain voltage. You let them go, and they go flying away. Okay? Now, we did this very briefly for gravity. We could plot force as a function of distance, and we get the following. And so, from R initial to infinity, we know that the work done is F dot dr, which is it's the integral, I should say. It's the area under. It's the integral of F dot dr. So remember, we could derive the gravitational potential energy of an object stuck in a gravitational potential well. It's negative gm on r. You could also do the same with Coulomb's equation, and it's a very similar equation. It's negative k q2 on r. Depends on the other charge influencing the other one. Okay? Or Q1, Q2, I should say. But that's not in the course, but just know that's the inverse square. Okay? So in year 11 level, you know, a charge of so many coulombs and so many coulombs determine the force. Let's kick it up a notch. Let's make our charges exist on a lovely right angle triangle. So let's just put our forces here. And I want to label them. Let's label them charge 1, charge 2, and charge 3. So each charge is going to be influenced by the other two. And if we know how far away the charges are and the magnitudes, we can figure out the forces, attractive or repulsive. Well, look, these are all positive charges, right? So they're all going to repel each other. So if I said, spawn these charges into existence and let them go, they're all going to go, zoom, you know, flying away, okay? But depending on the magnitudes and the distances, gives the magnitudes of the force, gives a net force on each. So let's just quickly sketch. Why do I keep putting my pen down there? Let's quickly sketch. Oh, let's go a little bit less than that. Here's my force that way, and here's my force that way. I'll call this one F1 acting on 2, and up the top, that's F2 acting on 1. That's like Newton's third law, action and reaction. Now let's consider these ones down here. This one would be F3 acting on 2, and over here would be F2 acting on 3, equal and opposite. And we're nearly done. We can then go, let's look at F1 acting on 3, and then let's go up here, F3 acting on 1. So now we've got two forces acting on each charge. So we could do top to tail method. I could say top to tail of my bottom corner, there's my net force. Oh, that's a F, not a... That's my net force on 2. Top to tail method over here, there's my net force acting on 3. And then up here, top to tail method acting on 1. Now, things get nasty because it's, well, two of them are nasty sums. Which force would be the easiest to find the net force on? 3. Why? They're at right angles, yes. So let's look at him. If we wanted to figure out him, well, we'd have to find angles, and then we have to do scalene triangles and then figure out sine and cosine rule. Things will start to get nasty. So let's just consider this guy down here, okay? Bit easier. So let's just go, the magnitude of F1 acting on 3 is going to be 1 over 4 pi epsilon naught Q1, Q3 over, they are separated by a distance of 3 centimeters. Okay? Okay, let's just write it out once more. So the Q values, what do we have? 1 millicoulomb times 2 millicoulomb over 4 pi epsilon naught times r squared. So guys, couple of things. Make sure you include the orders of magnitude if you're ever given this. As I said, you will not ever find a coulomb 5 centimeters from another coulomb. That would be lightning bolts and people dying. We can't get that much charge. So you are going to have smaller amounts. So Coulomb might have been playing with microcoulombs or pico or nanocoulombs. So you need to know your metric prefixes. They are in your data sheet. I'll write them down in just a moment. Also, centimetre. So hang on, back up a step. If you forget that, then your force is going to be 1,000,000 times too big. Because 10 to the 3 and 10 to the 3, 1,000,000 times too big. And then also, don't forget your centimetre. Okay? Many of you forgot the kilometre in the past test. Kilometres cubed, 10 to the 3 cubed. All right? So we've got to make sure you cube or square your metric prefixes as well. Or else your answer would be 10,000 times, no, try that again. No, 10,000 times too big. So, I'll get you to just evaluate that for me, and while you're doing that, I'll write out, what else do we want? We wanted F2 to 3. So now Q2 was 4, I believe, millicoulomb. Q3 was 2 millicoulomb. Make sure I got my charges right. Yes, I have. Over 4 pi epsilon. No, it's not. Let's write the value out. 8.85, 10 to the negative 12. And now the R value is 4 centimeters squared. Now, last year I did the 4.50. Last year I did the bottom right, which was a nasty scalene, but I know 2 to 3 is 4.50 times 10 to the 7 newtons left. I'm going to need a little bit of help.
10 to the negative 7.
10 to the positive. Yep. Because that's 10 to the negative 12.
Oh, okay.
So already we're up to 10 to the 6 divided by 10 to the negative 4, 10 to the up, big numbers, big numbers. Would somebody be able to help me with the top one?
I've got 2 times 10 to the 7.
20? 2? 2? 2. 1.99?
1.998.
1.998. All right. 2.00 then, times 10 to the 7 newtons down. So remember I said, you will be doing this a lot in the Year 12 course. You will be finding out, you're resolving your vectors into y's and x's and then summing them at the end using Pythag. Oh look, there's my metric prefixes. They can sod right off. So lastly, net force. Now again, I'm a bit lazy and I like simplifying. If they have the same order of magnitude, I reckon we could just go 4.5 and 2.00. At the very end, it would still have the same common order of magnitude. So the sum of all forces, square root of 4.5 squared times 2 squared. I'll do it. Is 4.92. We haven't gone over the order, so it's still 10 to the 7 newtons. And then theta arctan 4.5 on 2. 66.0. Okay, so lastly we could say that the net force acting on charge 3 is 4.92 10 to the 7 newtons down 66.0 degrees left. Okay. As I said, this is an unlikely scenario. It is not going to be possible to accumulate that much net charge so close together. Okay. The early 1800 entertainers, they discovered that if they wrapped these metal plates around an insulating foil, they could store charge. So they had made capacitors, and they couldn't even understand them. But they would take these capacitors to dinner parties where all the proper fancy royal British people, the noble aristocrats, would have their parties. And they would have these basic magic shows where they would get people to touch the capacitor and they would get a zap. And they're like, oh, jolly good, very good. And then they would suspend some bloke from a nylon rod. He'd accumulated a charge, and then he would be able to make little blue sparks. Oh, very good, very good. They had no freaking idea what was happening. but they were accumulating charge and then allowing, stored electrical potential and then allowing it to discharge and make these little zaps. And you might have done it with the Van de Graaff generator. You get all these aristocrats holding hands and they're all standing on an insulating thing, and then somebody earths themselves and everyone gets a zap. Oh, jolly good, jolly good. And then they drank wine and got drunk. That's it. Try this tricky one right now. So, please recall, you won't be getting coulombs. You will be getting metric prefixes of smaller amounts. Your data sheet, please recall, micro is 10 to the negative 6. Nano, milli is 10 to the negative 3. Nano, 10 to the negative 9. Pico, 10 to the negative 12. Going the other way, kilo, 10 to the 3. Mega, 10 to the 6. Giga, 10 to the 9. Tera, 10 to the 12. So, could you please zap? Could you please determine the net force on this bad boy here? You might wish to sketch in the two... Don't worry about the Newton's third law on the others. Let's just sketch in, okay, we've got an attractive force towards, let's call this charge 1, charge 2, and charge 3. So you've got a force towards 1, and then you've got a repulsive force away from 3. Okay, so I would like you to find the magnitudes of those two blue vectors using Coulomb's law and then combine them to figure out the net force. Again, conveniently, we've got an inside, that's red please, thank you, 120 degrees, but we'll worry about that later. Okay, so get going. Don't forget your metric prefixes for charge. Don't forget your metric prefixes for centi. Ooh, that's one that's not actually in your data sheet, but we need that. We need centi is the metric prefix of 100th. So add that to your knowledge bank.
So do you always use the absolute value of...
Well, yeah. Don't worry about adding positives. We could make a convention that if your final force is a positive, then that's repulsion, because that could have been a negative times a negative, or a positive. And if your final force value is negative, then that's attraction. But just look at the diagram and go, it's going to go that way. Yeah? So I don't need a convention for you to tell me that F3 is acting left and F1 is acting up 30 degrees in. Okay? Is anybody? Oh, Canberra. Oh. Does it do heart rate? Oh. Have you ordered your new band? eBay or JB? Yes, but you just have to wait 3 weeks for it. Nice. Campbell. Yes, you will need sine and cosine, I believe. No, just the magnitudes for now. You need to interpret the diagram that the F3 is repulsive, so going left, F1 is. Don't worry about. Just put the magnitudes of the charge. You then need to interpret whether it's going to be acting right or left.
Because the diagram it's attractive.
Yes. Well, in fact, it's up and 30 degrees right. Yes.
Or could you just say towards?
No. I'd go up 30 degrees right and left. Okay. What have we got? Q1, Q3. So we get 54.0 newtons up 30 degrees right.
So I think you've got to get it along with negative 19. Which is negative 25 as opposed to the negative 6. I got 54 also. I got 54, yeah.
I skipped a step because I'm lazy, but you can put the values in.
Yeah, so is it 1.6 times negative 19?
Yes, but this is 5 microcoulombs, which is 5 times 10 to the negative 6.
It should be negative 25.
It's not the fundamental charge.
No, it's not the fundamental charge. It's just that many of a coulomb. So if it was an electron or a proton, you'd use the fundamental. If it was a +2 ion, it would be 2 times the fundamental. And then this bad boy, I believe to be 43.2 newtons left. And now we go about F1 is 54. F3 is 43.2. So we get to this point and we need an internal angle. What do you reckon? That outside is 60. So I reckon parallel lines. Inside is 60. Boom. So now you've got your 2 side lengths. Two side lengths, 1 internal angle, away we go. Okay.
Cosine.
54 squared plus 43.2 squared minus 2a. Help me out here. $49.5. And then I reckon one of these bad boys, sine phi on 43.2, sine 60 on 49.5, times both sides by 43.2, take the arc sine. If I've drawn that to scale, it should be, it might be less than 90, I'm not sure. Help me out here. 49?
Yeah.
Okay. I'll take your word for it. Now, we don't want phi because that's the angle of the net force to one of the other forces. So what we want is this guy there. We want, let's call him theta because that hasn't been used yet. So theta equals 180 less 60 less 49.1 gives, I'm bad at maths, 70.9. I think.
Yes.
Cool. So finally, F2 equals 49.5 newtons. we could go left 70.9 degrees up. Okay? And so, at that instant, that is the direction that the second charge would accelerate. I haven't really drawn it on the diagram, but he's going to go that way. This guy over here is going to go probably that way. This guy up here, probably that way. Yeah? No? Yes? Don't know. You could figure out which charge is influencing it by more. It's definitely going down, but whichever one has the greater horizontal component determines the direction. So, have a think. If these charges were allowed to move, everything changes. The distance that they're from, and also the angles that they're from. So, you can only ever look at it in this snapshot. If you wanted to try and track this three-body system, you would have to do some computation where you would iterate every millisecond, move them, then figure out the force, then move them again, figure out the force, and they would track out and do stuff. They might fly apart or they might stick together. I don't know. I haven't really thought ahead that far. Test yourself, go home and do that, get mum and dad to give you 3 charges, and you can draw your own triangle. But let's get to electric fields and electric forces, because this will explain what I just said about those charges going flying out places. So, an electric field is a region in space, it turns out it can exist anywhere, even in a vacuum, where charges can be influenced by forces. The idea is that if you have charge, you're going to be influenced by an external electric field. It has to be external. You cannot be influenced by your own gravitational field. You can only be influenced by external, like the Earth or Mount Everest or the student next to you. So, the direction of the field is defined by convention. Highlight that for me, please. The direction that a positive test charge would move when placed at that point. So I like to consider my positive test charge as just a positive test charge on a stick. And if I place my positive test charge on a stick there, next to this other positive test charge, he's going to go straight the opposite direction. Coulomb's law would say he would be forced that way, and he would just go in straight line for as long as he's got the repulsive force. So, if I was to place him anywhere else... Oh, no, don't do that. Don't do that. No! My test charge. If I was to place him anywhere else... Well, we can start now drawing fields for charges. So the rule for drawing positive charges, you draw straight lines travelling away, because that is the direction that a positive test charge would move if you placed it there. Likely, what's the word I'm trying to get at? Likewise, similarly, contrary, oppositely to, if I place my positive test charge over here, he's going to go straight line towards the negative. So here's our convention. Away from positive towards negative. Someone just decided it to help us visualize fields and the direction that charges would move in those fields. So, let's now look at this guy down here, a dipole field. The field lines combine, and you will need to draw combinations of field lines for certain scenarios. Not too tricky, Rex, back up. Not too tricky, don't be sorry. Just be good. Okay. If I place my positive test charge here, right? Oh, let me try and draw him a little bit thinner. I'm zoomed in a bit. If I place my positive test charge there, he's not just going to go straight line to the positive, because at the same time, he's being repelled by him. So he would literally, if I could watch this in real time, he would fall in like something fall into a planet. He would go, and he would literally track along that field line, travelling in that curve. If I placed him over here, again, he would follow down and fall in like that. Because remember, that positive test charge is being influenced by two different forces, attractive of the negative, repulsive of the positive. Okay? So, next, there are other rules. Could we just, underneath, I'd like you to draw your own dipole electric field. So, obviously, it has to be symmetric. And I'll explain the symmetry in just a moment. So this one's nice because the positive of the the outwards line of the positive lines up with the negative line, the inwards line of the negative. You can also draw, oops, wrong way, try again, away from positive towards negative. But then in between, the field lines line up. And you'll find that in between you'll get more field lines. And they will always, the loops will always connect. What you need to be careful with, gentlemen, is it needs to be symmetric about both axes. So if I slice this about the vertical, that was supposed to be a highlighter, all right, then it's going to be symmetric on the left side, same symmetry on the right. Because the symmetry is going to represent a conservative field. That means that energy is conserved. If I move a charge in a certain region in one space, it does not gain or lose energy. That can occur if the force was to suddenly change. Imagine if you're standing on Earth and you fall into a well, you fall by a certain amount, you gain a certain amount of kinetic energy. If you go to another well and you fall into it and you suddenly accelerate faster and you gain more, that's a non-conservative field. You violated the conservation of energy. And so we need to draw symmetric field lines. Just before you depart, gentlemen, you can draw some, if you run out of, you can draw a few that could go out like that. But just know, which for every top right, you've got to draw the top left for your horizontal symmetry. And then for every top lines, you've got to draw your bottom lines for your vertical symmetry. Okay? Just know again that these lines do connect. Okay, it's just that I may have run out of page. If I put a test charge there on the line, the positive test charge is going to fall in, following that path. Okay, so just going back to the rules. The lines can never cross because the next important one that's tricky is that the density of the lines indicate the field strength. So your lines can come close together, which would represent a strong electric field, but they can never cross. Because what would two crossed lines represent in terms of density? An infinite field strength. So they can come really close together and they can be very, very dense in between the two charges. You've got lots of lines, but you can't have them cross. Okay? Also, we try to draw them leaving the surface of the object at right angles. As it says, Wace likes to deduct marks. If you're not drawing them at right angles, then you're not drawing them conservatively. Okay? So there are some examples of some conservative electric fields where all the rules of conservation apply. Okay? I will elaborate further on drawing field lines because it is an important part of the syllabus. I will see you all tomorrow. No homework. I'll give you some tomorrow. Hello.